Okay, I want to thank the organizer for inviting me and thinking about the bioinformaticians coming to this conference. So actually, I would like to start with some background to myself, since I'm not really used to this. So my background is and why I'm here. So actually, I'm not a crystallographer, but I love protein structures, and I actually have a crystal structure, which I'm really proud of. So I'm collaborating with experimentalists as well, so you can see my name here. And so I've been doing modeling for many years, but now I'm actually doing some proper modeling with using experimental data. Yeah. So back to my background. So actually, I'm doing protein structure bioinformatics for quite some time, and that's basically developing methods like this, and combining methods to. Let's see if I can just increase my. So I see what. So combining data analysis with bioinformatics, machine learning, and also doing like physics-based modeling and simulations. So I've been doing protein structure prediction methods. Now switching to protein interactions, protein peptide interactions, predicting disorder and transient interactions. And I've also been dealing with, this is the topic of today, protein model quality assessment since 2001 almost. So that's quite a long time. You realize you're getting old when you're like looking at your old papers, and it's like 20 years ago almost. So I was doing this at Stockholm University together with Arne Elofsson, and then I also, in the meantime, also a Rosetta development, because I did I spent a couple of years with David Baker at the University of Washington. So I also developed methods in the Rosetta package. So I participate actually in 9 CASP. This is also when you realize you're quite old. So the CASP is this, maybe you all but know that, because maybe you contribute with data to this benchmark of methods in structure prediction. And Rand has been an assessor here for quite some CASP. So as 9 CASP, it's CASP 5 to 13, so it's actually quite a long time. This is every second year, so you realize that it's a long time. It's every second year, so that's 19 years. And I have successful methods both in structure prediction and also, but mainly in quality assessment, basically, where our ProQ methods has been sort of top ranked in this benchmark ever since it was sort of introduced as a category. Okay, so that's why I'm here, basically. So I have this good method to evaluate local quality. So what is quality estimation? So here's a model. You don't really know anything about it. It would be good if you know which part is good and which is bad. And of course, it would be good if you generate ensemble of models or many models. It's also good to know which models are better, so you can rank the models. So you can predict both global and local quality. So here, for instance, is one example. This is from the latest CASP, I think. So this is one model in green, and then the native structure is in cyan. And you can see it deviates in this loop here, and also the first part is also deviating. And you can calculate here the C alpha distance here. Here is color-coded, so this is a bad part, and this is a bad part. And then we can see which part we want to improve. So how do we measure model quality? I think this is quite an important aspect of this, and one of the reasons we're also quite successful, because we early on realized that this was a problem. So, of course, I showed the previous slide, I saw model native C alpha distance. And that seems to be natural to use. However, that depends on the superposition, and it's not always obvious how to superimpose two molecules. So how many of you have used this align function in PyMol? I know this is a CCP4 conference, but maybe some of you are using PyMol as well to look at structures. And there's this align function. Many are using? You use it? Yeah. So many, I see some hands. So many have used this. Maybe you use the graphical interface, but then you can write some align. You have a model here, and you have a template here, and then you align. And what happens is that you get this error. If you look at the log again, maybe you don't do that, but if you look at the log in PyMol, you will see here like some RMSDs here. It's dropping in values, but then you also see it's reacting atoms, basically, or in the superposition. So what it's doing here is that it makes different superpositions by reacting what to consider to superimpose. So it reacts atoms that are bad, basically, all the time here. And then finally it ends up here. But then you only superimpose 641, but you started with 823. And basically, it's how we treat the bad regions that's the important thing here. So what PyMol does is this simple thing. It's sort of superimpose everything, and then it removes everything which is 2 angstrom. It's a parameter here. The default is 2. It removes everything, and then it cycles back until it reaches convergence or for a given number of cycles. So basically, you don't want to base your superposition on bad regions. Yeah. So that's the problem with bad regions, irregular RMSD. And then there are these other scores that have been developed also during CASP, for instance, and also Randa has developed some scores as well. I think this high accuracy was yours. Where you have this global, it's called GDTTS score. It's a global, called Global Distance Test Total Score, actually. And it's based on 4 superpositions, different superpositions, that tells you how many atoms can we superimpose under 8, 4, 2, and 1 angstrom. And then we take this average. And you have to divide by L, so you get some measure there. And then there's a high accuracy version here where you just have other cutoffs. And then there are other measures used, TM score, Sscore, MaxSub. They all basically develop based on this measure of downweighing residues that are far apart. So if the distance between between the correct and in your model is far away, you treat them as you give them 0 weight, but if they are close, they will get the weight to 1. So that was the superposition dependent one. But then there has been, of course, you don't have to superimpose structures to compare them. You can also compare internally distances. So then it's completely independent of this. So that, in a way, those measures might be more appropriate because then you don't have this problem, actually. So these are I just listed the dependent, but here are the independent. So you have LDDT, you're comparing local distances. Then it's also insensitive to domain arrangements like this. Because if superposition would superimpose one of these, right? If you do a superimpose it, we just take the larger one probably. And then there's also this CAD score developed quite recently, where instead of comparing distances, it compares surface areas. So in a way, this is actually maybe the more physical, realistic way of comparing things, because actually distances has problems. It's actually contact surface area is the actual physical interaction. So this is actually a really good method, I think, to compare things. And as I said, we have local versus global quality. So you can measure local quality of score. Then you will get like this profile across your sequence here, and then of course you can always take like the mean or making from these values calculate some kind of overall quality that you can use for ranking. So this was taken from the this is using LDDT. So you have a global LDDT of 0.61, and you can see it varies across the sequence here. And here is the structure. It's color-coded, where red regions are bad, like the standard dB factor. So if you check correlations between local qualities, the local quality measures, they do correlate. So the CAD and the LDDT, which are based on contacts or not based on superposition, correlate more. So you have this correlation here. It's higher between LDT and CAD score. And the ones that with the superposition correlate with each other as well. So your TM score and S score correlates quite well. So there's a correlation between the local quality. If you look at global quality, it's higher. So of course, there are more. If you look at the details, you can get more. There are more differences. But overall, these measures are really correlated. If you look globally, they are really correlated. But if you look at difference, because then now you're up in like over 0.90 in correlation coefficient for global measures. So protein structure modeling, this is something 101. This I took from the CS Modeler website. They have this tutorial on how to model things. And then this is the classical way of doing this. You have your amino acid sequence here coming in. You do so template search. If you don't find the template, you do like de novo ab initio modeling and stuff. And then you go on. And here is the validation part, the quality estimation. You do it after here. But this slide, I think, needs to be updated now, because in the recent years, there's been this new development with using evolutionary couplings. So there should be like a separate one here. You're doing template search. If you don't find them, you wouldn't do ab initio. You should really do this instead. So you should really do this evolutionary coupling analysis, multiple sequence alignment, and then you could actually build models even if you don't have templates. And this works fine if you have decent number of sequence homologs. And I actually saw in the program that Andrew will give a talk on this tonight from Deep9. And it's really like a third leg in this, I would say, or like fourth leg here because they have this hybrid thing. So it's really exciting for structure modeling that you actually can get this type of information by just having large sequence families. Okay, it works well. It's all, you can also check there are some other servers here. Okay. So how can you tell if a model is good or bad? Sometimes if these are your two models, you might lean to think that this is maybe the better one. It might be an easy case if you have these two models. But it might also be harder if they are quite similar. So these are two models, and if you superimpose them, they are very similar. If you add in the native structure, they are, it's also quite close to the native, but you can see that the green is closer to the yellow here. So the A is sort of 85% correct, and the other one is 70% correct, more or less. So we need a method to do this, of course. And you're familiar with this from PDB. You're familiar with this validation of structures. And this is sort of a validation, but it's a bit different. So, of course, you could do this. This could be like a quality estimate check. You could check for this. You could check for like Ramachandran outliers, etc., in your models. However, it's really easy to make completely wrong models that satisfy this PDB-like evaluation. Like more probability, you can easily satisfy, but a completely wrong model. So you wouldn't get so good ranking using this evaluation. But if you think about it, take one step back. So this is the lowest free energy structure. It corresponds to the native state. It's a classic energy funnel here. So if you just can estimate the free energy of protein models, we should be able to gain some insights into the quality of them. But the problem is that the models is not the native state. And you can see here that in this illustration, you have the native state here, and you have structures that are fairly similar to the native state, but are much higher in energy. So it basically means that a small structural change leads usually to large energy differences. So for instance, if you have clashing atoms overlapping, you wouldn't get a good description of it. So the quality estimate that you need to do needs to be robust to small structural changes. And this was realized early on as well. This is a quite old paper, one of the first maybe assessment methods from David Eisenberg. It's called Verify 3D. And it's based on the statistical preferences for amino acids in different environments. So you look in the PDB and see how common are, and the environment is based on burial and fraction of side chain area and local secondary structure. So basically, how common is it in the PDB, for instance, to have an alanine in helix conformation at a certain burial interacting with some fractional polar atoms? So if it's common, it's sort of good. If it's not common, it's bad. So you look for like preferences of this. This was a quite old method, worked quite okay. But we developed this a bit further, and we took sort of some of these ideas to describe the local environment around the residue. Okay, I can skip this. And took it a bit further. So if you think about this, it's some simple intuitive measures that correlates with local quality. So one of the things that should correlate is if the agreement between predicted and actual secondary structure, because we are really good at predicting secondary structure, so it's sort of 85% or 80% accurate. So if there should be an agreement with secondary structure. That's a prerequisite. So that's like an easy reality check. You can do the same thing for predicted surface area. That's also sort of the same thing, same accuracy there. You can check for conserved residues. Those should probably be better in a way. So if you do this, just a simple thing, you just try to correlate surface area with some quality measure, local quality measure. There is some. I mean, the correlation is low, but it's still it's not random. And if you do this is surface area and secondary structure and also conservation. Just that simple measure. And then you can combine them also using some machine learning. You can train a machine learning method to do it, and you can improve the correlation even further. But then we took this a step further. So instead of just using surface area and secondary structure, we also you add in residue-residue contacts, you have atom contacts, and you add in different features, and then you try to predict over a given window. So that's the description of the environment. And then over a given window that you slide over the sequence, over the structure, you're trying to predict whether it's a high quality or a low quality, using machine learning in that case. And what we could see, this was data from ProQ2, is that when you only train on atom, you get, this is estimated now by correlation, so it should be high. So the correlation to the true quality. So if you use just atom features, just atom contacts, so it's basically, you have a few atom types. So it's basically, then you get a certain correlation, but then in residue you get slightly more, because it's probably more information in the residue contacts, surface as well. Then you can combine these, and gradually you can improve performance by combining all these things. You're combining atom contacts, residue contacts, surface area, all the information you know, and then you end up with this correlation, which is fairly good actually, considering you're doing compared to the competition. And then we wanted to improve this, and we spent a large amount of time trying to improve this actually, because it's really hard to improve this correlation. And in ProQ3, we end up actually combining it with Rosetta Energy terms. So that was the best way we could come up with. So Rosetta, maybe some of you are familiar with the Rosetta Energy function. It actually has two energy functions, one full atom energy function and one more coarse-grained centroid energy function. So we wanted to use both those energy terms, and we took all the terms that we could sort of find, and then we calculate their local contribution, because the total energy function is the sum of all the terms, but we wanted to have the local contribution of each residue to this total energy, so that we could get the localized sort of score. And then if you just do the same thing, just correlation, you take the van der Waals score, that's sort of the contact, the overlap term, that correlates 0.13 to a quality measure. It's actually quite good. So this is all the different energy terms. This is one energy term, only one energy term in the Rosetta full atom energy function. Some might have a negative correlation, but then we have turned them around. And then this is the total energy correlation. So you can see already here, Rosetta's energy function is not as good as a dedicated quality assessor to predict this, because you have 0.33 and we had 0.71 for the free wells. And the reason is that it's so sensitive to small changes, most likely. So this is, you have the global, and you have the global there as well. And then we combine this using machine learning. So we take this, if you only train on this one, and then we train again on the window here, and then we can improve things a lot. So this is just for single things, not the window. So you see a local is just one, but then we can, if you look at the window, we get more information. So if you have a window of 5, we can improve correlation, and then we can improve it a little bit more, and we can take then a couple of windows, and then we improve it even further. And see, now we are reaching sort of the similar performance as we had for ProQ2, but only with this is on the Rosetta energy function, but sort of retrained. We get these two, and then we combine it again. Finally, we had terms we had from ProQ2, Rosetta, and this one as well. And then we can improve it even further. So ProQ3 combines all these things. And this was in the band. We compare it to some other methods. I mean, there are other methods also in CASP lately, but it's one of the top methods in CASP the last CASP. And then we realized we had spent like, I don't know, 2 years trying to come up with with this, how to improve it even more. But in the meantime, the deep learning was coming up as a field where it was actually useful. So we just took all the features that we had, all the features that we had, and they just, instead of doing, we were using support vector machines at the time. We were just using deep learning instead, and then we could actually. So here's the correlation we had with ProQ2. And then we just use deep learning. We improve it to 0.79, which is exactly the same correlation we spent 2 years improving, or 3 years, going from here to here. And then you could also improve this one by just, and the only difference here is that we use deep learning instead. And you can, maybe you think that this is a small change, but then you have to realize that improving large correlation is much harder. It sort of gets exponentially more difficult to improve a large correlation to improving a small correlation. So this is significant improvements. Okay, This is the performance. Here we have compared against CASP 11. We have different measures you can use. I think this is the best column. I should just have taken this one. This is the correlation per target. So you have one model, and then you have many models of this one. So this is probably the best. The per target is the one to use. It's the best measure, I think. And you can see that this is now also the whole history. So this is the first method we developed sort of 20 years ago. This is the correlation we had. And then ProQ2 was better, and then we had ProQ2, the deep learning methods here. And then I also added one of these ensembling methods here. So now we are sort of competing with this where these other methods that are using many models and compared to. So, and the input to this is just one model. You give it one model and you get the quality. So coming back now to why I'm sort of here is that these models the local quality estimate can be used to improve molecular replacement. So true model quality correlates with the success in molecular replacement. This is one figure of that. So you have quality here, and you have sort of this log likelihood gain LLG score from molecular replacement. You can see if you have a high quality model, you are more likely to have a high LLG. So if this is the model, you take a model from here, 50 GDT, you don't succeed here, or you have a low LLG, and then you add quality estimates to this, and then you do the same thing. And then the hope is then that you can actually improve these ones so that they actually can be useful. So here is a table where we show this. So this is I'm just showing the top here to illustrate what's in the table. So here is the target. This is the PDB code. This is the resolution of the data. There's a template, really low sequence identity template. And then this is two different models make in two different ways, and this is the percentage improvement of using quality estimates over not using it. So you can improve the LDGD for this particular case with 80% by just adding this quality estimates. And this was for one case. And then we did it for a number of cases, and you can see pretty much across the board you get the consistent improvement. There are some cases where you actually make it worse, obviously, but overall it's consistent improvement. So it should be really easy to use, and it's actually not that hard, because I think you just need to add these quality estimates to your B factor in your phasing model, and then it will sort of use these to downweigh different regions. So it's actually quite easy to get these RMSD estimates as well, because I have a server for the ProQ2, and this will actually just return. You give it your input model, and it will return a model with the error in the B factor column already. ProQ3 is also available as a server. ProQ2 is also implemented as a scoring function in the Rosetta software. So if you're running Rosetta, you can in principle just rescore it directly. Also standalone here. And then you can use this one also to predict different models. So acknowledgement. So Arne Elofsson and Carlos has been involved in the ProQ development, and this for funding. So, thank you.